Here we continue our discussion of software vulnerabilities. We'll talk about integer overflow flaws first, which are another type of exploitable vulnerability. An integer overflow occurs when a value exceeds the maximum representable value of the data type. So for example, if you have an unsigned integer that is represented using 8 bits, this is smaller than what you typically see, but let's say you have an unsigned integer, it's represented by 8 bits, and that integer is currently set to the value 255. And then in the code, the value 1 is added. 255 plus 1 is equal to 256. And this is what it would look like. You need a 9th bit in order to represent the number 256. However, this unsigned int only has 8 bits, and so the number 256 cannot be represented. What happens typically is that the number is truncated, and only the low order bits are kept. So 255 plus 1 equals 0. There are also integer underflows, which can also be dangerous. These occur when a value falls below the minimum representable value of the data type. So for a signed value, that would be below the minimum value that it can hold. For an unsigned data type, it would be any value less than 0. So here's an example of how integer overflows can be dangerous. The function handleLogin takes in a user ID and password and checks if the password is valid. But it only allows 6 attempts. After that, it locks out the user. On line 2, the variable attempts is incremented. Attempts is a global variable, and for the sake of this example, assume that it is a 4-bit signed integer. On line 3, the code checks that the number of attempts is less than or equal to 6, the maximum number allowed. If so, then on line 4, the password and user ID are checked, and if they are correct, the global attempts variable is reset to 0, and the user is granted access. Otherwise, on line 7, the user is denied access. So far, so good. But what happens if the user uses up their 6 attempts with unsuccessful tries? On the 7th attempt, the branch condition at line 3 will fail. The number of attempts will be greater than 6, specifically it will be 7, and execution would jump to line 7. How about on the next attempt? On the 8th attempt, the attempt variable again gets incremented on line 2. 7 plus 1 equals 8. But remember, this is a 4-bit signed integer. 7 is represented in binary as 0, 1, 1, 1. Adding 1 to that gives the binary value 1, 0, 0, 0. And in a 4-bit signed integer, 1, 0, 0, 0 represents the decimal value -8. So in line 3, the branch condition will succeed. -8 is less than 6, and execution will continue to line 4. The user gets to keep trying guesses. Here's another example of how an integer overflow vulnerability can cause harm. The function takes 2 parameters, shown in line 1, a pointer to an array of integers and the length of that array. In line 2, a pointer to an array called myArray is created. This is going to be used to create an array of integers. In line 3, memory for the array of integers is allocated. The call to malloc here is saying, allocate an amount of memory equal to len times the size of an int. Let's say an int is 4 bytes, which is typical, and len is 5. This will then allocate 20 bytes of memory. But let's say the length len is not 5, but instead a very large number, a number close to the maximum value that can be represented by an int. That large value multiplied by 4 will overflow the maximum possible value. And when that happens, the overflowed value will be some very small number. So malloc will allocate some small amount of memory. If we go down to lines 6 and 7, we see a for loop that is copying the contents of the input array into myArray. The for loop will copy up to len values. But remember, the space allocated for myArray is very small, much smaller than the large len value. A lot of memory past the end of the malloced myArray will get overwritten. So this is an example of an integer overflow attack being used as a stepping stone to launch a buffer overflow attack. And it's worth noting that the code is seemingly smart and careful. On lines 4 through 5, the code is checking that an array is indeed allocated, and the code only copies in len values. On first read-through, it looks like it is making all the right checks. Finally, an integer underflow can also cause problems. If you had code that allowed an integer underflow to occur, the underflow would result in a negative value, which, when converted to the unsigned parameter to malloc, would get interpreted as a very large unsigned int. The attempt to allocate an enormous memory block could trigger out-of-memory conditions or return a null pointer if memory is unavailable. Another type of vulnerability can arise from race conditions. A race condition occurs when two or more processes have access to the same resource, and the final state of that resource depends on the relative timing of the two processes. This can be a problem if some of those possible final states are erroneous or undesirable. So here's an example of a race condition. Let's say Purple has a bank account and uses an ATM to withdraw cash. So Purple walks up to the ATM and says they would like to withdraw $100. The ATM has to query the bank to see what the balance is for Purple. So the ATM sends a query, get balance, to the bank. The balance at the bank is $900, so the bank sends back to the ATM, balance equals $900. The ATM will do some check. Is the amount requested $100 less than the balance available? And it is. And so then the ATM sends $100 to Purple. Purple gets their $100. And then the ATM has to send another message back to the bank telling the bank to update the balance. And so the ATM will set the balance. 900 minus 100 is 800. So the ATM sends set balance 800 to the bank. And now the bank maintains a new balance, which is 800. Now let's see what happens if Purple and Orange share a checking account. Purple and Orange both walk up to separate ATMs at around the same time, and they both want to withdraw money from their shared checking account. So Purple walks up to the ATM and says, I'd like to withdraw $100. At around the same time, Orange walks up to some other ATM and says, I'd like to withdraw $50. Both ATMs have to query the bank to find out what the balance is, so they each send a get balance request to the bank. The balance is $900. The bank responds to each request with balance equal to 900. And so each ATM checks that there's sufficient money for the funds requested. The Purple's ATM will spit out $100 for Purple. Orange's ATM will spit out $50 for Orange. And then the two ATMs have to update the balance. So Purple's ATM will calculate 900 minus 100 equals 800 and sends a message to the bank, set the balance to 800. Orange's ATM will calculate 900 minus 50 is equal to 850 and sends a message to the bank, set the balance to be 850. So the bank, what is the final balance for the bank? Well, the balance will be either 800 or 850, depending on which message arrives last. But it should really be equal to 750 because a total of $150 has been withdrawn. Here's another example of a race condition. So here you have some code. The file name, the variable file name is set to the actual name, temp name. And then later on in the code opens up the file for writing using the open call file name, and it says open, create the file, and open it for read-write access. Let's say there's another process running. The attacker is controlling that other process. The attacker is able to guess at the name temp name and creates a symbolic link from temp name to the password file. So now the name, temp name, is now an identifier for the password file. When the first process runs, which is a privileged process, it follows the link and opens and writes to the password file. The attacker's process did not have privilege to open the password file. The attacker would not have been able to open the password file for reading or for writing. The first process did have that privilege, and the attacker was able to trick that process into opening the password file for reading or writing by leveraging a race condition. So a particular type of race condition in which the gap between checking permissions and using the permissions can be exploited is called a time of check to time of use attack, and it's often abbreviated as TOP2. So here, the check is happening in the system library. This code is executed whenever the user calls open. And so in that first line, you see the file name with write access is checked. If that check goes through, so it's the check makes sure that the process does have sufficient privileges in order to open that file for write access. If that file goes through, then the code will open up the file for write access. However, an attacker could have a separate process running. And in between the time between when that file is checked and when the file is open, the attacker can unlink the file name, so it removes that name, file name, and creates a new name to point to the existing password file. Again, creates a new link that points to the existing password file. So now, when the first process goes to open that file for write access, it is actually opening the password file. So the key to any type of race condition is that two entities have access to the same resource. The next kind of vulnerability that we'll talk about is backdoors. So backdoors are a point of entry that bypass existing access control measures. Typically, they are added for testing or maintenance purposes, and usually they grant complete access to the system. They're often added after the standard code and security review processes, and they allow easy access for maintenance or for testing. But it's a safe bet that once this portal exists, it will be discovered at some point. And once it is discovered, anyone can use it to gain unfettered access to the system. And if you look at the code, this is terrible. The password is hard-coded into the program. But this is not an exaggeration of what actually happens. Things like this are done all the time. We're going to end with a discussion of privilege escalation at a high level and what it means. So an attack is very often done in stages. First, buffer overflow may be exploited to allow the attacker to run some code of their choosing, but often that first exploit is just a stepping stone to the full exploit, a foothold or point of entry into the system. To accomplish the goals of the attacker might need more privilege, and this is achieved through privilege escalation. So often, first a buffer overflow is executed to gain entry and give foothold, from which to launch the privilege escalation attack, then the privilege escalation, and then finally the full payload of the attack is executed. The vulnerabilities that we've seen all lead to some form of privilege escalation. So for example, escaping the fixed functionality of a program, being able to launch a shell, that is an example of privilege escalation. So is escaping a sandbox to access the full file system, gaining root level privileges, gaining kernel mode privileges, getting the system to open up a file for which the attacker would not otherwise have permissions. These are all examples of privilege escalation. Okay, we'll stop here.